Hello and welcome to our presentation. This is Pradyun and we are a group of fourth year ECE undergraduates. Let me introduce my team members. We have Debajit, Shivansh and Nivedita Maji. As you can see, the name of our project is Automated Electric Vehicle Delivery System. As the name suggests, we are inspired to solve the problem of delivery systems by the use of automation and mapping between two set points. Some of the problems that are faced by current delivery systems are human error, involvement of heavy manpower, unexpected collisions, and very inefficient methods of distribution. We intend to solve the said problems by mapping the shortest possible path by preventing collisions between delivery agents. Now, let me explain out what our problem statement is. On a given map with several start and end points, we tend to design an automatic delivery system with n number of delivery agents. This process is to be done without collisions of delivery agents and is to be done with a path that takes minimum cost. Now, let me move on to the logic used for the implementation of the said problem statement. We have used search algorithms to look for the shortest path from start to end point with given obstacles. We now have an established grid and have used a heuristic approach to find the best path for the delivery system. Now let me explain how we have mapped it out entirely. Our entire system is mapped as a graph. Each point in the graph corresponds to either a start point or an end point. Each node is now connected with an edge which indicates the direction of movement. The equidistant points correspond to equal costs in the graph. Obstacles are associated to high edge costs, which make them completely undesirable in our path. Now, after this is completely mapped out, we simply apply enhanced versions of breadth first search and depth first search to solve the above constraint. We take the help of heuristic based algorithms to generate better and faster results. Now, I'm passing on the batter to Nivedita to take over.
So I'll be going with the A-star algorithm. A-star is a computer algorithm that is widely used in pathfinding and graph traversal. The algorithm efficiently plots a walkable path between multiple nodes or points on the graph. On a map with many obstacles, pathfinding from a point A to B can be difficult. However, the A-star algorithm introduces a heuristic into a regular graph searching algorithm, essentially planning ahead at each step so a more optimal decision is made. A-star is an extension of Dijkstra's algorithm with some characteristics of BFS. Like Dijkstra, A-star works by making a lowest cost path tree from the start node to the target node. What makes A-star different and better for many searches is that for each node, A-star uses a function f of n that gives an estimate of the total cost of a path using that node. Therefore, A-star is a heuristic function which differs from an algorithm in which a heuristic is more of an estimate and is not necessarily provably correct. A-star expands paths that are already less expensive by using the function f of n is equal to g of n plus h of n, where f of n is our total estimated cost of path through node n, g of n is the cost so far to reach node n, and h of n is the estimated cost from end to goal. This is the heuristic part of the cost function, so it is like a guess. The calculation of h of n can be done in various ways. The Manhattan distance from node n to the goal is often used. If h of n is equal to 0, A star becomes Dijkstra's algorithm, which is guaranteed to find the shortest path. Using a good heuristic is important in determining the performance of A star. The value of h of n would ideally equal the exact cost of reaching the destination. This is however not possible because we do not even know the path. We can however choose a method that will give us the exact value some of the time, such as when traveling in a straight line with no obstacles. This will result in a perfect performance of the A star. Now let's move on to the code. There are three functions in our code. Init for initializing the environment, setting the goal, and adding the Manhattan distance as the heuristic method. The reconstruct path function regenerates the path start to goal using the came from array. The third function is the search function, which searches within the graph using the heuristic to find the best path for traversal. The time complexity of A star depends on the heuristic. In the worst case, the number of nodes expanded is exponential in the length of the solution, but it is polynomial when the search space is a tree. Now over to Shivansh for explaining CBS algorithm.
The A-star algorithm that Nivedita talked about does not work with multi-agent pathfinding systems. For multi-agent systems, we use the CBS algorithm. The CBS algorithm, that is the conflict-based search algorithm, is a centralized algorithm. It is a joint agent model where a specific model deals with all set of agents and nodes. This multi-agent pathfinding algorithm is a two-level algorithm. At high level, a search is performed on conflict tree, which is a tree based on conflicts between individual agents. It represents conflicts and constraints within a tree and runs much faster than the A-star algorithm talked before. At low level, fast single agent searches are performed to satisfy the constraint imposed by high level constraint nodes. Let us run to an example to understand how this algorithm works. Within the example, we first find the individual paths by low level without talking about conflicts or constraints. Within these, we look for conflicts within the answer. As you can see in the example, we see a conflict that at the same time, both of these are at V2 on the third time. We resolve these conflicts by adding constraints in the next level where we provide only one system can be at that specific point within the next time frame. We then find for solutions satisfying these constraints. Once we get those solutions, we look for conflicts within these solutions again. And we keep on repeating the same process until we find the solution with minimum cost such that we have the satisfaction of minimum constraint. Within the code for the same, we define an algorithm with dimension, agents, and obstacles, defining the environment that we work upon. We define the valid state and is goal that are representations of the valid states and the goal of our requirement. We define the conflict and constraint class to define the conflicts and constraints to work within an example. We define the get neighbor function to find the neighbors at a specific point that are valid from that specific neighbor. We get the first conflict for using the first conflict function. And from this conflicts to generate constraint to move to the next step, we use the create constraint from conflict function. We then use a basic search algorithm that works within the entire tree searching for the best result. The results can be seen in the report for the same. We, for the CBS algorithm, work with 2 agents, 10 agents, and 20 agents in an obstacle-based environment. As you can see in the report, it gives non-collision and optimized path for each agent. These has used applications once we are working in industries, manufacturing industries, or travel within small areas. I now move the banter to Debajit to continue.
Hello. Now we will present the idea for the third idea of our algorithm, which uses a decentralized approach, which is the hybrid velocity approach. So what is different in this approach is that instead of a centralized execution such as CBS, here every agent acts on its own and devises its own path based on the velocity of the other agents. Also, it assumes that the other agents have half responsibility, like it's in doing the same thing. That's why it is known as a hybrid velocity obstacle approach. So the vehicle obstacle is a set of all the velocities of the robot that will result in a collision with another robot at some future point in time. So that gives us a set of possible velocities for all the agents. The agent in our algorithm will actually make use of this fact in later steps. Unfortunately, this concept does not work well for the multi-agent systems because every agent is actively adapting to its own velocity to avoid the other robots, but it is also assuming that the other robots never change their own velocities. Hence, that's why we need to use two different concepts and merge it into one hybrid approach. The reciprocal velocity obstacle approach is very simple, and it thinks that the other agent also shares the same responsibility in avoiding the collision. Hence, its responsibility itself is halved. So finally, as we can see in this diagram, that this is initially just the vehicle obstacle diagram. This is the reciprocal velocity diagram, and this is the hybrid reciprocal velocity diagram. So what it does is that it has the consequence that if an A robot A is trying to pass through the path of B and they are actively colliding, like in this case, and we have no other solution in the normal by individually using the vehicle obstacle and reciprocal velocity concept, what it does that it gives a slight push in the opposite direction for the reciprocal velocity of one agent, thus making it easier for the agent A to go in one direction and agent B to go in the opposite direction, thus avoiding conflicts at the maximum. Now we will move on to the code. The code is very simple, and So we have a very basic simulate function is just for creating the video, and the compute velocity, what it does is that it computes velocity based on the union of all the other agents velocities. And it also uses some other functions like check constraints and create constraints, which it does when we are actually having a conflict in our solution. So then it creates constraint and resolves it. And finally, we will be moving on to the results. The results can be seen here, and as we can see that this agent is acting independently without interacting with the others, but it assumes one thing, that the others also know and share the same responsibility as it is. So in our conclusion, we can see we can see that the decentralized approach actually works a bit slower than the centralized approach, as it assumes and has to perform much more computation than the CBS has to do, because the CBS is a two-level tier hierarchy, and it makes optimal use of the low level and the high level searches. The velocity obstacle approach is a bit slow because it acts independently, and we can see that all the techniques were able to perform well, and it solved a problem of multi-agent pathfinding in the electric vehicle domain, and the references are as below. Thank you.